Welcome back to the second lecture of this three-lecture series. And for those of you who just joined, missed the first lecture, so let me take a few minutes to summarize what I discussed and what we learned. So I talked about how pollutants and other greenhouse gases gets transported around the planet so fast that these gases surround the planet like a blanket. Then I talked about how this blanket traps the heat radiation from the Earth and then leads to global warming. And I also pointed out that we know within about 25% how much heat, how thick this blanket has become by our pollutant gases and how much heat it has added. And so those are all deduced from observations. That's a key thing to remember. Then we discussed about how much warming it should have caused. It was predicted and how those predictions were proved to be right in terms of the warming. And then we just touched on the observations of evidence for the warming. And then I conclude the lecture by saying that the gases should have already warmed the planet by about 2.5 degrees, but we have only seen a third of that. And the balance, I said, is about 20% of that additional warming is still in the oceans, and the oceans will cough it up in the coming decades. Then I talked about half of the warming has been masked by particles, sulfates, nitrates. And then I also talked about a smoke in the blanket. So these particles which act like mirrors on the blanket. Then I said we're also adding black carbon, which is soot, and it traps heat sunlight. So that's where we left. So what we're going to talk about now in this lecture is what are the impacts? How much has the climate already changed? How is it impacting us? And what do we expect if the planet indeed heats up further as it should? So let's start with that. It's not advancing. Is this not activated? Oh, that's there, sorry. Yeah. Okay. So that's the second lecture, impacts of climate change. So let's again, start with what's been observed. This is global average surface temperature or near surface temperature of the planet. It includes land and oceans. It includes the ice-covered areas. It includes the northern hemisphere and southern hemisphere. That's what we mean by globe. And you see, if you look at the overall trend, the planet has warmed in the last 100 years by about 0.7 of a degree Celsius. Okay? And it shows the warming trend, with time. And if you look at all of the model simulations, particularly from this Intergovernmental Panel of Climate Change, the conclusion you get is about half to 0.6 of a degree of the total, or 0.75, cannot be explained without this additional greenhouse blanket. Okay? So let's see what else is changing. How has the planet changed? So many of these data sets we don't have before the 80s or before the 60s. Sea ice goes back to 60s, and clearly this is the September, that's when the retreat is maximum. The sea ice has gone from about, this is in millions of square kilometers, sea ice extend from 9 to drop to below 5. Okay, it's a huge rapid change. In fact, that's probably one of the iconic changes as far as climate change is concerned. And this was, by the way, forecast by models decades ago on theories. The other is to go hand in hand with this Arctic sea ice disappearing is the warming of the surface air temperature, where the warming in some parts of Arctic exceeds about 2 degrees. And this is from NASA's Earth Observatory, normally a conservative institution in terms of these things. And even they say some parts of central Siberia warmed as much as 6 degrees. So this half a degree, 0.6 degree global average, we shouldn't fool that into thinking everywhere it's warming by 0.6. Okay? So where is the other region? The warming is very large, close to home for you guys, the Tibetan Plateau. And we don't have data for the eastern and central Himalayas, and I would suspect that's doing the same thing. So I'm going to show you some record. This is called the third pole because it is the largest ice mass next to the, the Arctic. Next to the Arctic and the Antarctic. So let me just show you the data from the Chinese region. So this is published by the Chinese Academy of Sciences, okay? And it was an alarming data, the data they have collected over the Tibetan region. What they find is the trend increases from about 0.1 degree per decade as they go up the mountains to when they reach the peak, the warming is about 5 times large. So the warming is increasing with altitude, and mind you, it's per decade. So half a degree per decade in this period means about 2.5 degrees, just like what we are talking with the Arctic. Okay? So the snow-covered regions are warming a lot more rapidly for a good reason. And we looked at this problem in a paper we wrote in 2005 to see what is the difference between surface temperature change and this upper air temperature change as we go up. And we found that warming, of course, is pretty close to the China, but my work was all on the Indian side. So clearly, both sides of the plateau are warming at the same rate. So this was the work we found microwave satellite. Later, Gautam and others, he was from IIT here, and then he's at NASA, and he sort of confirmed our findings, all happening, rapid warming on the Indian side. There's something I'm going to touch on later. Then we try to simulate with models. How much of that we can explain? It turns out only half of the warming we can explain with greenhouse gases. And we can't explain this with just greenhouse gases alone. We needed to add the smoke in the blanket. I need the blanket to thicken, but that's not enough. The black carbon, okay? But at this stage, I would say it's a proposal, a hypothesis, okay? In science, I need to understand, results have to be repeatable, but no matter who is doing it, no matter which model you use, and which data you use. Reproducibility is the key thing in science, okay? This has been reproduced by 2-3 groups. That's not enough. We all could have made the same mistakes. But nevertheless, the greenhouse models cannot explain this warming. That, I feel confident saying that. We have looked at many models. Something else you need to add. So going on, I wanted to now focus on South Asia. Why is warming such a big deal in the tropics? Okay? The first thing is, as we all know and expect, this shows the ocean temperature, sea surface temperature. The hottest ocean is the Indo-Pacific warm pool. It's called a warm pool, it shouldn't mislead you, is that about most of this region is hovering around 1 degree temperature within each other. Once the planet, the oceans reach about 29 degrees Celsius, it doesn't warm more, but it just expands, okay? And that sea surface temperature, without too much exaggeration can say holds the pulse of the planet, particularly the tropics, for an important thermodynamic reason. You need to understand this, and before we understand the impacts of what all this means to the tropics. Okay? It goes back to this Mr. Water Vapor feedback we all talked about. Remember I said the blanket thickens, it warms your body, you start evaporating more moisture, you here meaning ocean, evaporating more moisture, and the moisture thickens the blanket further. As one empirical evidence, I told you about how the humidity increases from the poles to the tropics, observed humidity, mind you, by a factor of 25 to 30 because of the vapor pressure increase. What we are trying to do, if the planet warms by 2.5 degrees, and if you follow the saturation vapor pressure, that's the exact scaling I've done, that's where we are pushing the system. So this whole thing will move to the right. And where you are, if you are sitting here in India, you will be there in a 2-degree warming. So what does that mean? Okay? So I'll just say in as simple a term as possible. I've left this diagram, maybe you can think about this. In the atmosphere, carries energy. Temperature is one form of energy, right? Sensible energy. The other form of energy the air carries is potential energy. That is, when it goes up, it has more energy. It can drop in gravity. Third is called latent energy, the energy contained in the water vapor. See, vapor takes the energy from the ocean, goes to the air, and when it rains, it releases that heat to the air. So that's how the atmosphere and the ocean talk to each other. One of the ways, through water vapor. It so happens the reason you have such deep convection and monsoon and cyclones in India, the tropics, is because your potential temperature, or the energy carried by each water molecule, is very large. So that is why when in summertime or in the tropics, you form these deep cumulonimbus clouds. Once they lift up, they're like hot air balloon. They goes up till they reach an energy barrier. Okay? The important thing is, when the actual temperature increases by 1 degree, the latent energy increases by 2, and the total increases 3 times. So don't get fooled when you say the tropical ocean has warmed by 1/16 of a degree. The energy to the power of the storms has increased to a factor of 3, by 2 degrees. Okay? So moving on this curve by, if a 2-degree warming will go to 6 degrees, and you're going to go higher. What does higher mean? Everything gets more intense. Okay? So I'll tell you, do you see evidence for this? So this is the equation for those of you who want to track it down. I'm not going to walk you through this, but feel free to look at it and email me if you're stuck in this equation. So do we see this evidence for this intensification? There was a famous paper written by Dr. Goswami. He is now the director of the Indian Institute of Tropical Meteorology, Pune. And he took this region, it's all data collected by Indian observing system. He found the moderate rainfall has decreased. That's the area I'm working on. But he found the heavy rainfall is increasing. And the very heavy is increasing even more. No matter what is causing it, this is a double jeopardy in terms of monsoon, water, because the heavy rainfall doesn't recharge the ground. It just runs off. It's the moderate guy, falls in, percolates through the soil. Okay? So the most likely explanation, the more thermodynamically, physically concerned explanation is that is caused by the warming we are seeing. More latent energy in the system, it's powering more storms. Okay? But I'm not ruling out other explanations, but this is the one which has withstood the test I put in terms of, is there a physics which can explain it? You can always hand wave and say, oh, it's just natural variability. When nothing else fails, everything fails, you can blame it on Mother Nature. But there is always laws of physics which is determining these things. Okay? And the other thing, which is a little bit also concern, is that equatorial Indian Ocean, amongst all the oceans, is warming the most rapid. It has warmed by about 6/10 of a degree. If you just imagine the amount of massive energy carried by a body of water, this warming goes up to 200-300 meters. So you can just imagine, right? Just go out and look at the ocean and think about the vast area of that, and the whole thing is heating up. So the equatorial Indian Ocean, but the North Indian Ocean is not. I'll come to that later. So these are all just walking it through observed evidence. I already talked to you about the rainfall shifts. Okay? The key thing in all this is this a variability last 50 years and it'll go away, or is it going to get worse? China, you see this flooding, is preparing for the fact that this is going to continue. It's not natural variability. Okay? How do you know that? This is, one of my students is doing excellent work, Yang Angshu, he's from China. Chinese are building diversion, huge pipes to take water from the south to the north. Because the north is where all the action, the Beijing and this and that, they're all drying out. Is this one way we're going to adapt to climate change? Okay. So what's happening in India, I think now there has been numerous studies from Indian meteorologists. They're all acknowledging, yes, the monsoon is decreasing. Okay, this was a study from IIT Delhi group, Professor Dash. So he has confirmed, what Goswami said, the heavy rainfall is increasing, moderate is decreasing, by and large. Of course, there are exceptions, okay? So all India, heavy is increasing, moderate is decreasing. I'll talk to you later about why the moderate is decreasing. So I showed you the brown clouds over Los Angeles, and since I'm focusing in India, I'm seeing this, you can see the Indo-Gangetic plumes during the dry season. So these mirrors and smoke in the blanket happens primarily in the dry season, starting from November to April and May. Okay? And some of the heavy pollution, you think about this, of course, is due to emissions, but the other thing, which is that if you look at the emission of things like soot, it's not that large compared to the US, about 30% larger. But if you look at the atmospheric concentration of black carbon, it's a factor of 3 or 4 more. So why is that? Okay, some is transported, but the other main reason is during the dry season you don't have rainfall. Things accumulate. The major way, you know that, right? When a rain comes, the sky looks blue. So what we call wet removal is the major way the atmosphere has to clean all the junk we put in. Unfortunately, in the tropics, you have a long dry season. That's one of the important reasons why pollution builds up. Okay? So, I wanted to talk about this briefly. That shows the major soot emissions. It happens everywhere in the planet. Here we have estimated how much is that blanket getting heated directly by that black carbon. So that's that. But because the black carbon is intercepting sunlight, it cuts the sunlight reaching you. So that's the dimming. Okay, you can see it's maximum, largest in China. This is all savanna burning in Africa. Okay? So the major source of soot emissions, like you see in the US, is diesel. In places like South Asia, it's diesel plus residential biomass combustion. Okay, and then open burning contributes too. China is residential combustion, but not biomass, coal combustion. So the first thing this pollution does is heavy pollution. This is a picture from Beijing. And as far as India is concerned, I'm just summarizing the work which is done in my lab and few other labs. And this has been shown by a group at Berkeley, and WHO confirmed this, about 500,000 deaths indoor from inhaling cook stove emissions, okay, with smoke coming out. And then this thing goes out, and outdoor impacts. And we have shown, as well as a group in IIT Bombay and the Stockholm University, roughly 60% of this pollution comes from indoor residential combustion. The key thing to remember there is they're not doing this to pollute the planet. They have no access to any of the fuel. They're sort of forced to use it by sheer poverty. Okay? But I'm going to talk to you about we can use this as an opportunity to help them. Cleaner energy, access to clean energy. So this thing destroys crops, the ozone, and then the black carbon gets deposited in the snow, darkens the snow, melts the snow, and we find the black carbon effect, as far as the glaciers are concerned, is about comparable to the greenhouse gas impact. And then the dimming of the sunlight cuts down evaporation of moisture from the ocean. And we are saying that's the reason the monsoon, the moderate rainfall, is slowing down. But this needs to be confirmed. Only 2 other groups have been able to reproduce our results. Other groups with different results, they say in fact it intensifies the rainfall. And we are now forming a scientific working group. Tomorrow we are going to meet of half a dozen expert institutions under the TERI University umbrella and see if we can get into this in a serious way. So moving on, let's talk about the glacier melt. Turns out, this is a study by my colleague Tim Barnett, first published in Nature 7 years ago. 1/6 of the world population gets water from snow melt. It is threatened in a warming world, okay, the hatched areas. Of course, India also depends on the glacier melt, but rainfall dominates it because this is the glaciers fed Ganges and Brahmaputra and Indus. That's why this region is covered. But let me take you to California, where I am. We are suffering the worst, one of the worst. See, it turns out California, our water, much of California is from snow melt. Okay? And when you warm, what happens? The snow melts early in the season. We need our water in the summertime. So by summer, our water has depleted. And the ground is also not high because this early melting of the snow pushes everything. As a result, we have more frequent forest fires. That's one of the things not talked about, forest fires from this climate change. And so much so, 4 years ago, I had to evacuate my house. The fire had come within 1 kilometer. There was nowhere to go, so I packed up with my family and went into the beach thinking we'll jump into the water if the fire. It's amazing, living in a superpower. You're still not ready for things like this. And so forest fires is one major hazard. Let's talk about close to Himalaya. This is the paper which came out just 2 weeks ago in Current Science. They're talking about alarming retreat of glaciers in Sikkim. Okay? The glacier has retreated about 2 kilometers from 60 to 2008. And see what happens when the glacier melts, it builds up this moraine lake. And when the lake level exceeds a certain height, it just breaks down and flooding downstream. It's called glacier outburst flood. And they map it out beautifully in this paper. Okay? So that was the extent of the glacier in the 60s. Now with the glaciers retreated and this lake is expanding. So when it retreats further, the lake is going to become too big for its own good. So it'll just flow down, break through. So I want to point out one of the vulnerable regions to climate change, the planet, is this so-called third pole, the Himalayan glacier system, because it's receiving multiple stressors. Remember, natural change. There was a little ice age, and that time all the glaciers built up over 400 years ago, and we are recovering from that. So that's a natural retreat from that. We are adding to that the land dust. Dust is also an absorbing aerosol. Greenhouse warming, the atmosphere. We saw how the warming elevation. Then the black carbon, heating the air and depositing on the snow, so far and so forth. So this is something, it'll be worth a massive, major, multi-institutional study to look at what's happening in the Himalayas. Okay, not on a micro scale, the entire region, because it's seeing global greenhouse gas. Remember, about 75% of the warming is coming from greenhouse gases from the developed nations. Okay, so that abuse is there, and then on top of that, we are adding locally, and there's natural change. So, what is the stability of the system? Does it have enough resilience to withstand this, or is there some breaking point here? Okay. And I just want to point out another study of all this as far as droughts in India. This is by Dr. Gosain from IIT Delhi. He is talking about from baseline to mid-century areas, all these are areas where the number of drought weeks will expand. Okay. So the other thing I want to talk about is extreme events. So if you look at, just take for example, where we are, Delhi, right? And your temperatures vary from cold to what we call normal and to hot, depending on the month, depending on the season, depending on year to year. Some years are cold, some years are hot. But when you warm entire Delhi from global warming, you're shifting this curve to the right. Does that make sense to you? The whole thing is getting warmer. So as a result, what we call heat waves, the frequency will increase significantly. Extreme hot days will increase. And this is seen everywhere in the planet. So these are the so-called extreme heat waves. This is the European heat waves. And it's talking about how the frequency is increasing, okay, in Australia, North America, everywhere. You're experiencing more hot days, okay? And add the heat and then early melting of snow. So by summer to fall, you've created a perfect recipe for wildfires. Of course, part of the fire in California is mismanagement too. Okay, but so I want to take you back again. This thing I showed in my lecture 1, and wanted to remind you again. What is this? I talked so far about what's happening now. Now I want to see what might happen in the future. Our first anchor point is this interglacial to glacial cycles, warm, cold, okay? And the last interglacial was about colder by about 5 degrees. The tropical oceans were colder by 5. That's what glaciologists claim. And now we are talking about 2 degrees from there, okay? So that's where we have to start relying on our models to figure out what that 2 degree warmer planet is going to look like. The first thing is sea level. Okay, this is the observed record of sea level, and it's accelerating, just like the warming is starting from the 30s. Sea level was increasing 2 millimeters per year, increased to 2.1. Now it's standing at 3 millimeters. So why is sea level increasing? First, that same reason the mercury in our thermometer rises if you have fever and you put it in your tongue, because they expand. Okay? So the water heat, remember I said the heat has penetrated to about 700 meters in the ocean. So the whole ocean is warming and it's expanding, thermal expansion. The other is melting of the glaciers. Okay? It's a landlocked ice which will cause increase in the sea level. Sea ice doesn't do that. So the glaciers, particularly the Greenland glaciers, the Alps melting is contributing to this, and the Antarctic is also starting to melt. That's the reason they claim that it's accelerating. This red data, these are all surface data, which is not really homogeneous. We don't have these tide gauges everywhere in the planet. Whereas this satellite, the last 20 years is from data is from space, and that seems to corroborate the surface data. Of course, increase in sea level, the deltas, saltwater intrusion, of course, will have agriculture impacts. So I want to remind you again about my forecasts and recommendations. We have already dumped enough gases to warm the planet by 2.5. Even if you reduce CO2 by 50%, the warming will still be larger than 2.5. I will show that in the third lecture why I am claiming this. But if you think then, what does this really mean? It means if we don't do anything, it'll be even worse. Okay? So at the minimum, it looks like we have to prepare to adapt to 2.5 degree warming, even if we cut CO2. Okay? Or there's something else we can do. I'm going to pick it up on third 3. So that is what I'm going to show is that we will very likely reach 2 degree warming by 2050 if all we did was cut down CO2. But again, I want to point out, I'm not talking about we shouldn't reduce CO2. The only way we are going to avoid catastrophic warming is reducing CO2 emissions. And that has to be done now because of its long lifetime. Okay, let me give you an example. We are putting about 40 billion tons of CO2 every year. Okay? Half of that stays in the air. So if we delay our action by 10 years, we would have put another 400 billion tons. I mean, it's just a massive issue. So the CO2 reduction has to start now because of its long lifetime. So don't misunderstand me. I'm not saying there is something else other than that. What I am saying is if all we did was CO2, we'll still reach 2 degree warming. How do we avoid that? Okay? So let's talk about what does this 2-3 degree warming for India, for Asia means. This shows the population size will be impacted by cyclones. Okay? So the circles are proportional to the number of people affected. So the max, and it gives you how many thousands. Okay? So obviously, if cyclone intensity would increase, we're not talking about frequency, but intensity, Asia would be the most affected. And of course, we are talking about 1 meter rise in sea level. The upper extreme is 2, the lower is 0.5 meter. Most of the low-lying Maldives. I've been going to Maldives last 15 years. I have an observing station. I almost do a field study almost every year in Maldives. I was there last March. They'd certainly go down. I built my observing station at 20 meters. So I'm hoping my observatory will survive at least till 2050. And other tropical Pacific Ocean islands. So most of them would be sacrificed so that I in the US can drive my car. Okay? So we have to think about the justice of all this. I mean, that's a new branch of science which is coming out. I'm not involved in that. The former Prime Minister, President of Ireland, Mary Robinson, has started a huge effort, NGO, and I'm going to be in a public event with her next week around the same time on this climate justice issue. And the sea level impact, of course, Bangladesh just sticks out, okay? And the Nile Delta, Mississippi, you heard about our Christina, how it wiped out that whole city. So these are all some of the major vulnerable regions. They talk about medium, high, extreme. I just want to tell you, all these things I don't believe, because we just don't know what kind of instabilities would be triggered with a 2 degree warming. This is based on our model understanding, okay? I mean, when I say I don't believe, I'm saying we might have underestimated it or overestimated. We don't know that. So that is as far as the impact part of it is concerned. And I just decided to focus on few things which are relevant here. If I were to give this talk in the US, it'll be totally different. And the reason I and others of my scientists have gone to do is focusing on the global warming is not getting the public just interested or involved, because they think there is a planet which is called globe, it's happening somewhere, right? The global change is nothing but summation of individual changes. So the big move is now to understand what is happening in our region. Okay? So for example, one of the things we like to see a scientific study done by scientists on what does a 2-degree planet mean for India or for South Asia, because it's connected. Okay? Such studies exist, but they use the models we do in the US. The models are geared towards those who build it. So our models are focused on getting because that's where we have access to data. So these kind of models have to be built here nationally. So you know what processes are important, what has to be included, and then we use that model to assess here what it means. And honestly, I would say there will be major surprises. And also scientifically new discoveries to be made, focusing on that scale. So that's something I'm pushing for, each nation doing its own assessment, not using the models done in America or UK, but you build your model here and put the things you know is happening here. Tune them based on your observations and then run them loose for the future. So the question which we need to address is, what can be done to cope with global warming? Can we adapt to this? Okay? Or should we, if we figure out, no, we cannot adapt to such changes, then we redouble our efforts to mitigate it. So that brings to this question, can it be limited or mitigated? Remember, I'm telling you we already committed 2 degrees warming. Is it too late? So another question I'd like to see the panel question take up is, what would we do if it turns out it's too late, the planet is going up 2.5 degrees, sea level is going to do this? What is it we can do or we would do? Right? Remember, if it gets hot, we can always pack up and move north. Is that what we would do if it's too late? So these are some of the issues we should think about. And the thing I already, can we adapt and prepare for its worst imagined effects? So these are some of the things I'll pick up in the next lecture. And of course, I want to thank my students and postdocs. It runs in tens and colleagues in hundreds. But this particular lecture, I want to thank Professor Charlie Kennel, my colleague at Scripps, and my graduate student Christina Pistone and Yang Yang Xu, who they helped put this part of the lecture